10 American torpedoes raced toward 3 Japanese aircraft carriers near Truk. The firing position was excellent. The range was close. The targets were enormous. Lieutenant Commander John Scott expected devastating results from USS Tunny. Instead, his crew heard explosions too early. Most detonations occurred roughly 50 yards before the torpedoes reached their targets. One carrier suffered only minor damage. The others continued toward Truk. The attack happened during April 1943. American submarines had already spent 16 months fighting across the Pacific. Their crews had reported an alarming pattern from the first weeks of war. Torpedoes passed beneath targets without exploding. Others struck steel hulls and produced only a dull metallic sound. Some detonated before reaching the ship. Many attacks appeared tactically perfect. Yet the expected wreckage never appeared. Commanders initially searched for human explanations. Perhaps captains had estimated range incorrectly. Perhaps nervous crews had mishandled delicate equipment. Perhaps inexperienced officers were exaggerating their failures. The weapon itself carried an impressive reputation. The Mark 14 represented years of secret American development. It was designed to attack the strongest part of a modern warship indirectly. Rather than striking armored sides, it could travel beneath the keel. A magnetic exploder would sense the ship overhead. The warhead would then detonate below the hull. Water pressure would transmit the blast upward. The ship might break under forces its armor could never stop. That was the theory. The concept was technically ambitious and potentially devastating. It was also protected by extraordinary secrecy. Secrecy limited realistic testing before the war. Production torpedoes were expensive and available in painfully small numbers. Tests usually employed exercise warheads instead of complete combat assemblies. No full program fired production weapons beneath representative targets under wartime conditions. Individual components appeared successful. The entire system remained largely unproven. That distinction became deadly after Pearl Harbor. American submarine crews entered combat, believing their principal weapon had already been validated. The Bureau of Ordnance shared that confidence. When patrol reports contradicted expectations, the reports threatened years of institutional judgment. The easiest explanation was operator error. But the Mark 14 did not possess one isolated weakness. It carried several major defects. Each defect produced different symptoms. Worse, correcting one problem exposed another hidden beneath it. The first problem involved depth. Combat torpedoes commonly traveled about 10 feet deeper than their settings indicated. A weapon set to pass just beneath a keel might pass far below it. The magnetic exploder might never receive a strong enough signal. The torpedo would continue harmlessly into open water. Submarine captains responded by selecting shallower settings. That improvised correction sometimes brought the weapon closer to its intended depth. It also changed how the magnetic system behaved. A stronger magnetic influence could trigger the exploder too soon. That is what confronted Tunny near Truk. Scott had compensated for one suspected defect. His adjustment revealed another. 7 torpedoes that might have struck the carriers exploded prematurely. The resulting blasts sounded convincing inside the submerged submarine. Japanese records later supplied the missing perspective. The explosions had occurred before impact. They produced noise, water columns, and little meaningful damage. This was more than a failed attack. It was a controlled demonstration created by combat. The submarine reached an effective firing position. The torpedoes followed useful tracks. The targets were present exactly where expected, yet the weapon defeated itself. Even then, the deepest defect remained concealed. Disabling the magnetic feature would not make the Mark 14 reliable. A direct impact could still fail. In fact, the straightest and apparently best hit could be the worst possible hit. The reason was hidden inside a small contact mechanism in the torpedo's nose. Its failure would transform one Japanese tanker into an unwilling test target. That encounter would finally force the Navy to confront an impossible conclusion. The submariners had been right. The Mark 14 entered war carrying assumptions inherited from controlled peacetime trials. Its depth mechanism seemed dependable because exercise torpedoes appeared to behave correctly. Combat torpedoes were different. A live warhead added weight and changed the weapon S-balance. The depth system also measured pressure from an unsuitable location on the body. Water flowing around the moving torpedo distorted the pressure reaching that mechanism. The resulting error drove the weapon deeper than its crew intended. This was not obvious from inside a submarine. After firing, the captain usually watched the target through a periscope. He could see the ship and perhaps the torpedo wake. He could not directly measure the weapon's depth beneath the surface. A silent passage under the target resembled a faulty magnetic exploder. It could also resemble poor aiming. Several possible failures produced the same result: that uncertainty protected the weapon's reputation. During the opening months of war, submarine commanders repeatedly questioned their own calculations. Some reduced the selected running depth. Others fired additional torpedoes at targets that should have required only one. A limited wartime supply disappeared into attacks, producing no visible damage. The consequences extended beyond wasted weapons. Every extra launch increased the chance of detection. Every additional minute near an escorted target brought depth charges closer. A submarine might reveal its position without disabling the ship it attacked. Unsuccessful captains also faced professional judgment. Aggression, accuracy, and command ability were easier to question than a secret technical system. The Bureau of Ordnance defended the weapon using its existing test history. From its perspective, inspected torpedoes had passed established procedures. Reports from combat lacked controlled measurements. They described outcomes, not laboratory conditions, but operational evidence continued accumulating. One of the clearest early challenges came from Rear Admiral Charles Lockwood. He assumed command of submarines in the Southwest Pacific during May 1942. Lockwood had received too many similar reports to dismiss them separately. He wanted a test that could leave physical evidence. His staff arranged for USS Skipjack to fire torpedoes through a fishing net. The net was suspended vertically in calm water near Frenchman Bay in Western Australia. A torpedo passing through would cut a visible hole. The holeless position would reveal its actual running depth. The method was simple. It avoided arguments based on distant observations during combat. The first results were disturbing. Weapons set for shallow runs cut the net substantially deeper than expected. Further shots confirmed the pattern. The discrepancy was not a minor adjustment. A torpedo could travel roughly 10 or 11 feet below its selected depth. That difference could place it completely beneath a merchant ship. Lockwood now possessed measured evidence rather than frustrated patrol reports. He sent the findings through the command system. Even then, acceptance did not come easily. The Bureau questioned local testing methods and environmental conditions. Its engineers repeated tests under their own control. Those trials eventually confirmed that the depth problem was real. The explanation involved both calibration and hydrodynamic pressure. The depth mechanism had been tested and adjusted under conditions that did not reproduce the complete combat weapon accurately. Its pressure-sensing arrangement compounded the error once the torpedo was moving. Corrective changes followed. The sensing and calibration system was modified. Crews also received revised guidance for depth settings. A major defect had finally been isolated. But the apparent solution produced a new wave of failures. Torpedoes now traveled closer to their intended depth. That should have improved magnetic detonations beneath enemy ships. Instead, submariners reported more premature explosions. Some weapons detonated before reaching the target. Others exploded almost immediately after launch. The depth error had previously carried many torpedoes below the strongest magnetic field. By correcting depth, the Navy had placed them where the magnetic exploder's weakness became harder to ignore. The first defect had masked the second. Earth's magnetic field varied across operating regions. Ships differed in size, heading, construction, and magnetic signature. The exploder was expected to interpret those changing conditions inside a moving torpedo. Its pre-war development had never tested enough realistic combinations. Now the Pacific itself was conducting those tests. Each failure placed an American submarine inside the experiment. The magnetic exploder promised an answer to increasingly difficult naval protection. A conventional torpedo struck the side of a ship. Armor, internal bulkheads, and protective blisters could absorb part of that explosion. A blast beneath the keel behaved differently. The pressure wave lifted the hull from below. The resulting gas bubble then collapsed beneath the unsupported structure. This sequence could bend or break a ship's backbone. Achieving that effect required the torpedo to recognize a vessel without touching it. The Mark VI exploder attempted this by detecting changes in the surrounding magnetic field. A steel ship disturbed that field as the torpedo passed underneath. Once the disturbance crossed a threshold, the firing circuit activated the warhead. The principle was sound. Its wartime implementation was unstable. Magnetic conditions were not uniform across the planet. A setting developed at one latitude could behave differently elsewhere. Target size and heading also altered the signal. Electrical components faced shock, vibration, moisture, and manufacturing variation. The exploder had to distinguish a real target from misleading changes around it. There was little room for error. If sensitivity was too low, the torpedo passed beneath the ship. If sensitivity was too high, it exploded before reaching the hull. Pacific submarine crews encountered both outcomes. A premature explosion sometimes persuaded attackers that they had scored a hit. Sound traveled efficiently through water. Inside a submerged submarine, an early detonation could resemble an explosion against the target. Crews often had to dive before confirming results. Escorts then filled the area with depth charges. Under those conditions, careful observation became impossible. American intelligence gradually found another source of evidence. Intercepted Japanese messages described torpedoes exploding short of their targets. Those reports came from the receiving side. They could not easily be blamed on American range estimation. Submarine commanders increasingly requested permission to disable the magnetic feature. Some had already lost confidence in it. The Bureau of Ordnance remained reluctant. The exploder was secret and represented a major investment. Disabling it meant abandoning the weapon's intended under-keel advantage. It also meant admitting that pre-war testing had been inadequate. Operational commanders faced a different calculation. A theoretically powerful system was worthless if crews could not predict its behavior. A simple contact explosion against the hull seemed preferable to an advanced explosion in empty water. Rear Admiral Lockwood continued gathering patrol evidence. After moving to command Pacific Fleet submarines, he pressed the issue more forcefully. The attack by Tunny strengthened his case. Japanese communications confirmed that several explosions had occurred before impact. The failure could no longer be explained entirely through American observation. Lockwood presented the accumulated evidence to Admiral Chester Nimitz. Nimitz accepted the operational argument. On June 24, 1943. Pacific submarines were ordered to deactivate the magnetic exploders. The Southwest Pacific Command soon followed the same course. The Mark 14 would now depend on direct contact. This decision removed one source of premature detonations. It did not produce the expected reliability. Torpedoes began reaching enemy hulls without exploding. These failures were especially confusing because some impacts looked perfect. A torpedo striking squarely should have delivered maximum force to the contact mechanism instead. The geometry of that impact could prevent detonation. The defect involved a small metal firing component inside the exploder. Upon impact, the mechanism had to move quickly enough to release the firing sequence. But a direct collision created enormous deceleration. The surrounding structure distorted under that force. The firing pin assembly could bind before completing its movement. An oblique hit imposed less severe loading on the vulnerable parts. It could therefore detonate more reliably than a perpendicular strike. The ideal tactical hit had become the worst mechanical condition. Crews did not yet possess a controlled demonstration of this contradiction. That evidence arrived aboard USS Tinosa. Its captain, Lieutenant Commander Lawrence Daspit, found a large Japanese tanker in July 1943. The target offered almost laboratory conditions. It was damaged, slow, and difficult to miss. Tinosa fired repeatedly. The torpedoes ran correctly. They struck the tanker. Most refused to explode. Daspit preserved his final torpedo and returned with evidence the Bureau could no longer explain away. On the morning of July 24, Tinosa sighted Tonan Maru Number 3 west of Truk. The Japanese vessel displaced more than 19,000 tons. It had once served as a whaling factory ship. Japan had converted it into a naval tanker. Now it was carrying fuel along a route revealed by American codebreakers. The tanker initially presented a difficult angle. Daspit maneuvered Tinosa into position and fired 4 torpedoes. 2 missed or passed without effect. 2 struck near the stern and exploded. The damaged tanker stopped and settled lower in the water. Its propellers were no longer driving it away. No escort immediately forced Tinosa from the area. The target remained afloat. Daspit approached for what should have been a routine finishing attack. Tinosa fired another torpedo from close range. The wake ran directly into the tanker. A tall splash appeared against the hull. There was no explosion. Daspit tried again. Another torpedo struck. Again the warhead remained silent. The stationary tanker now offered an exceptionally clear firing solution. Its range, bearings, and speed were not changing unpredictably. Tinosa's crew carefully checked every setting. They examined the fire control solution and verified the torpedoes before launch. Then they fired repeatedly. Each wake traveled toward the same broad steel hull. Observers saw impacts. Sound operators heard the torpedoes stop at the target. The expected detonations never followed. Daspit altered the point of aim along the tanker's side. He varied the attack geometry where possible. The result remained unchanged. By the end of the encounter, Tinosa had launched 15 torpedoes. 13 reached the tanker, only 2 detonated. 11 direct hits became duds. The episode stripped away nearly every convenient explanation. The target was not maneuvering. The range was short. The firing solution had been checked repeatedly. The torpedoes were no longer using their magnetic feature. They were making physical contact with the ship. Something inside the contact exploder was failing at impact. Daspit refused to expend his final torpedo. That decision preserved a physical sample from the same production group. Tinosa left Tonan Maru Number 3 damaged but still afloat. The tanker was eventually towed to Truk. It survived an attack that should have destroyed it many times over. Tinosa returned carrying its last torpedo and a meticulous patrol report. Daspit's evidence reached Lockwood during August 1943. The admiral reacted with anger but also with a demand for proof. He ordered tests using torpedo exploder mechanisms and a heavy steel plate. The method reproduced the sudden deceleration of an impact. An exploder was dropped from a measured height onto the plate. The first tests confirmed Daspit's report, at impact speeds representing a square hit. The firing mechanism often failed. The problem centered on the contact exploder's firing pin assembly. The original firing pin was relatively heavy during a direct collision. The torpedo's nose stopped with tremendous force. The exploder's structure could deform under that load. The heavy pin experienced resistance before moving through its required path. It could become trapped before striking the primer. A perfect perpendicular impact produced the most violent deceleration. That made binding more likely. An angled impact spread the deceleration differently. The mechanism had a better chance of completing its movement. Submariners had occasionally noticed that glancing hits seemed more successful. Now the observation had a mechanical explanation. Lockwood's team needed a replacement that could move rapidly before the surrounding structure distorted. Workers at Pearl Harbor developed a lighter firing pin. They used lightweight metal associated with aircraft propeller construction. Reducing the pin's mass reduced its inertia. It could complete its motion faster during impact. Repeated drop tests showed a dramatic improvement. The modified mechanism was simple compared with the original magnetic concept. It did not restore the under-keel attack promised before the war. It made direct hits explode. By late 1943, corrected contact mechanisms were reaching submarines. After nearly 2 years of combat, the Mark 14 was finally becoming dependable, but the delay had already shaped the Pacific submarine campaign. The Mark 14 crisis was not simply a story about defective hardware. It was also a failure of testing, communication, and institutional trust. Each technical defect had survived because the complete weapon was rarely tested realistically before the war. Torpedoes consumed a large share of limited ordnance budgets. Destroying one during a live trial appeared wasteful. Recoverable exercise models offered a cheaper alternative. They carried recording equipment or exercise heads instead of operational warheads. That substitution changed the weapon being evaluated. The combat head was heavier. Its weight affected depth and balance. Its exploder introduced components absent from ordinary practice shots. A successful exercise run therefore proved only part of the system. The torpedo could leave its tube. It could follow a heading. It could pass beneath a target. Those achievements did not prove that a complete combat weapon would detonate correctly. Security created another barrier. Knowledge of the magnetic exploder was tightly restricted. Many submariners entered combat without extensive practical understanding of its limitations. Maintenance personnel could inspect only the areas covered by authorized procedures. Patrol reports traveled toward organizations already committed to the design. The system separated the people experiencing failures from those controlling technical acceptance. That separation influenced how evidence was judged. A laboratory measurement carried official authority. A Captain S report contained uncertainty. Combat offered poor conditions for controlled observation. Targets maneuvered and escorts attacked. Periscope estimates could be wrong. Crews could misidentify ships or mistake internal explosions for torpedo hits. Those uncertainties were real. They also became reasons to discount a remarkably consistent pattern. By the middle of 1942, Pacific submarines had fired hundreds of torpedoes. Their results remained far below expectations. Some commanders compensated by firing larger spreads. That practice increased the chance that one weapon might function. It also accelerated shortages. A submarine carried a finite number of torpedoes into waters thousands of miles from its base. Once those weapons were gone, the patrol's offensive purpose was largely finished. A dud, therefore, consumed more than its own purchase cost. It consumed fuel, crew endurance, intelligence, and a rare firing opportunity. Japanese merchant shipping was especially vulnerable during the war's opening phase. Escort systems were incomplete. Air coverage remained uneven across enormous sea routes. American submarines could penetrate areas where surface forces could not operate safely, yet their primary weapon reduced those advantages. Ships that escaped in 1942 could carry troops. Fuel and raw materials again. The exact losses caused by defective torpedoes cannot be reconstructed with certainty. Not every claimed hit was genuine. Not every functioning torpedo would have sunk its target. Weather, tactics, maintenance, and crew experience also influenced results. The broad effect remains unmistakable. American submarines repeatedly reached attack positions without receiving dependable results from direct hits. The crisis also damaged command relationships. Some submarine captains were judged insufficiently aggressive. A few were removed after unsuccessful patrols. Not every criticized commander had performed well. However, defective weapons made fair evaluation much harder. A cautious captain might conserve unreliable torpedoes. An aggressive captain might fire many and still return without confirmed sinkings. Statistics alone could not distinguish tactical failure from mechanical failure. Lockwood approached the problem differently. He treated repeated operational complaints as evidence requiring experiments. The fishing net transformed an invisible depth error into a measurable hole. Japanese messages distinguished premature explosions from actual hits. Tinosa converted contact failure into a sequence of nearly identical trials. The drop tests then reproduced the mechanism on land. Each step reduced uncertainty. The decisive evidence did not emerge from one dramatic accusation. It came from connecting field observations with simple physical tests. Once the contact exploder was corrected, submarine performance improved sharply. Better radar, intelligence, training, and tactics contributed to that improvement. So did growing numbers of submarines and expanding maintenance support. The repaired torpedo was not the campaign's only changing variable, but crews could finally expect a correctly aimed weapon to function. That confidence changed how attacks were planned. It also exposed how much opportunity had been lost while the weapon's reputation remained stronger than its evidence. Repairing the Mark 14 required more than changing parts at a distant factory. Submarines were already operating from bases scattered across the Pacific. Their torpedoes came from different production batches. Depot crews needed instructions, replacement components, gauges, and time. Every modification also had to preserve safety inside a crowded submarine. A torpedo warhead could not be treated like an ordinary machine assembly. The exploder was normally installed only when the weapon was prepared for combat. Safety devices prevented detonation during handling and the first portion of its run. Any improvised change had to leave those protections intact. The earliest operational response had been adjustment rather than repair. When crews suspected deep running, they selected shallower depths that helped some attacks. It also increased the danger of a torpedo breaking the surface. A visible wake could alert the target and reveal the submarine S-bearing. Rough water made the result even less predictable. After the magnetic exploder was disabled, crews changed their aiming philosophy. They no longer sought an invisible passage beneath the keel. They needed the torpedo to intersect the ship's hull. Target draft became less important than securing physical contact, but the faulty contact mechanism created a tactical paradox. Submariners were taught that a square impact offered dependable activation. Testing showed the opposite. Until improved firing pins arrived, commanders were advised to seek more oblique impact angles. This was a temporary workaround. It asked crews to alter a firing solution around an internal defect. An angled hit could help the exploder function. Too great an angle could cause the torpedo to glance away. The captain had to balance these risks while estimating target motion through a periscope. The lightweight firing pin removed much of that contradiction. Its value came from speed rather than strength. A heavy pin resisted rapid acceleration because of its greater inertia. During impact, the surrounding structure could crush or distort before that pin completed its travel. A lighter component moved sooner. It reached the primer before deformation trapped the mechanism. The change illustrates how a small object can control an entire weapon system. The Mark 14 weighed thousands of pounds. It carried a large explosive charge and a complex propulsion system. It depended on gyroscopes, depth controls, and calculated target data. Yet all that machinery became irrelevant if one small pin failed to travel a short distance. The replacement did not require a larger warhead. It did not require more speed. It required a better understanding of forces lasting only a fraction of a second. Production changes followed the field solution. Corrected exploders gradually replaced or modified defective units. Crews still had to maintain torpedoes carefully. Gyroscopes required inspection. Air systems needed proper charging. Depth and steering mechanisms demanded accurate adjustment. No torpedo became immune to every malfunction. The critical difference was predictability. A weapon could now be tested against known standards with realistic expectations. By early 1944, the Mark 14 had become a dependable combat torpedo. Its basic propulsion and guidance had never been the central scandal. Those systems could carry the weapon over useful distances with substantial accuracy. The failures had concentrated in depth control and detonation. Once corrected, the same overall design became highly destructive. American submarines intensified attacks against Japanese shipping. Radar supported night surface approaches. Code-breaking helped place submarines near valuable routes. Wolfpack tactics concentrated boats against convoys. Improved torpedoes allowed those advantages to produce actual sinkings. Japan responded with escorts, aircraft, route changes, and defensive measures. However, its maritime economy depended on long and exposed supply lines. Tankers were especially valuable. Industrial production and military operations required oil transported from southern regions. Every successful torpedo attack tightened that logistical pressure. The repaired Mark 14 was now helping produce the campaign its designers had imagined. Its transformation did not come from a revolutionary redesign. It came from accepting evidence that the original design had failed. The Mark 14 is often remembered as one defective weapon with one obvious solution. The historical sequence was more complicated. Its major failures appeared in layers because each depended on different operating conditions. The depth error dominated early attacks. A torpedo traveling far below its setting might never approach the intended detonation point. Its magnetic exploder could therefore remain silent even if that exploder was also defective. Correcting depth increased exposure to magnetic irregularities. Premature detonations then became more visible. Disabling magnetism finally forced weapons into direct impacts. Only then did the contact mechanism fail often enough to produce undeniable patterns. This layering helps explain why individual patrol reports were difficult to interpret. A miss could mean incorrect range. It could mean excessive depth. It could mean a failed magnetic signal. An explosion could be premature or correctly placed. A direct hit could still become a dud. The crew observing from one restricted viewpoint rarely knew which event had occurred. Several defects could even appear within one attack. That complexity does not excuse the delayed response. It explains why realistic testing was essential. Testing separate components under favorable conditions could not reveal their interactions. The full weapon needed to carry a combat warhead. It needed to travel at operational speed. It needed to approach representative steel targets from different angles. It needed trials across varied magnetic regions and sea conditions. Finally, investigators needed to recover or examine failures whenever possible. The pre-war program did not combine these requirements adequately. Cost played a powerful role. A complete torpedo destroyed during testing had to be replaced. Budgets were limited during the interwar years. Production capacity was also restricted. Saving weapons appeared responsible when war remained a future possibility. That economy transferred the cost into combat. The Navy eventually fired valuable torpedoes under conditions offering little useful measurement. A failed shot during a controlled trial could expose a defect. A failed shot beneath an enemy escort might reveal almost nothing. Secrecy also protected the Mark 6 exploder from broad scrutiny. Its intended effect depended on surprising an enemy. Detailed knowledge was therefore confined to a limited group. But secrecy reduced the number of engineers, technicians, and operators able to challenge assumptions. It also discouraged realistic fleet familiarity. A hidden system can preserve tactical surprise. It can also preserve technical mistakes. The Bureau of Ordnance was not staffed by people seeking failure. Its engineers had designed difficult weapons under severe constraints. They possessed test data, supporting their confidence. Their mistake was treating that evidence as stronger than repeated combat results. Institutional responsibility made reconsideration painful. If the weapon was defective, earlier acceptance decisions had been wrong. If the weapon was sound, unsuccessful attacks belonged to submarine crews. The second conclusion initially fit the existing paperwork more comfortably. Operational commands developed the opposite bias. They saw patrol after patrol return with similar complaints. They also watched skilled captains lose opportunities under dangerous conditions. Their evidence was imperfect but persistent. Lockwood's importance came from bridging these worlds. He did not rely only on anger or reputation. He ordered physical tests that technical authorities could repeat. The net test measured depth directly. Captured enemy communications documented premature explosions. Tinosa supplied a preserved torpedo and a nearly stationary test target. Drop trials isolated the contact mechanism. This sequence converted experience into engineering evidence. It also demonstrated that frontline improvisation needed formal validation. Setting torpedoes shallow could compensate for depth. It could worsen magnetic behavior. Seeking angled impacts could reduce contact failures. It could also reduce the chance of hitting at all. Workarounds kept submarines fighting. But they could not replace corrected hardware. The final solution required cooperation across commands, depots, laboratories, and manufacturers. Once that cooperation accelerated, fixes arrived within months. The tragedy was that the same urgency had not governed the first warnings. By the time the Mark 14 became reliable, the Pacific War had changed. American submarines were more numerous. Their crews possessed greater combat experience. Forward bases shortened voyages into Japanese-controlled waters. Radar allowed boats to find and approach targets at night. Improved intelligence directed patrols toward important shipping routes. Reliable torpedoes connected these advantages into one effective system. A radar contact alone could not sink a tanker. A decoded route could only create an opportunity. A skilled approach merely placed the submarine within firing range. The torpedo had to complete the final journey during the early war. That final link repeatedly broke. After the corrections, successful attacks became more consistent. Submarines moved closer to Japan's home waters. They attacked merchant convoys, tankers, transports, and warships. They also laid mines and performed reconnaissance. Some rescued downed airmen during operations near enemy territory. Their central strategic effect came from attacking maritime transport. Japan's empire connected distant sources of oil and raw materials with factories at home. Those connections depended on ships. A tanker required specialized construction and could not be replaced quickly. Its loss affected more than one cargo. Every future voyage disappeared with it. The survival of Tonan Maru Number 3 therefore carried consequences beyond one patrol. The vessel represented scarce transport capacity. 11 functioning contact exploders might have destroyed it in July 1943. Instead, Japan recovered and repaired the tanker. It returned to service before being attacked again later in the war. One defective mechanism had preserved a valuable enemy asset. Similar escapes occurred without such complete documentation. Many cannot be reconstructed confidently. Submarines sometimes claimed ships that had survived. Other targets disappeared without witnesses. Japanese and American records do not always align cleanly. It would be misleading to assign every early failure to the Mark 14. Command errors happened. Target speeds were misjudged. Torpedoes missed for ordinary tactical reasons. Counterattacks disrupted firing solutions. Mechanical maintenance varied between boats and bases. War remained uncertain even after the technical fixes. Yet the documented failures establish a substantial pattern. Weapons ran deeper than selected during controlled net trials. Magnetic exploders detonated prematurely in attacks confirmed by Japanese messages. Contact exploders failed during repeated impacts against a stationary tanker. Drop tests reproduced the binding mechanism. These were not legends created after the war. They were separate defects supported by different forms of evidence. The weapon's later success provides another important comparison. The Mark 14 was not inherently useless. Its propulsion system offered useful speed and range. Its guidance could deliver accurate tracks. Its warhead was powerful when it detonated. Correcting depth control and detonation unlocked capabilities already present in the design. This made the early loss of opportunity more painful. American industry eventually produced large numbers of weapons and replacement parts. Training, maintenance, and tactical doctrine improved alongside them. Japan's anti-submarine response never fully neutralized the growing threat. By 1944, merchant losses were placing severe pressure on fuel distribution. Warships could exist in port while lacking enough fuel for sustained operations. Aircraft training and industrial movement also suffered from shortages. The submarine campaign had become a strategic blockade conducted beneath the ocean. The repaired Mark 14 contributed directly to that transformation. Its history, therefore, contains two contrasting weapons within one metal body. The first was advanced in concept but unreliable in combat. The second was mechanically corrected and operationally devastating. The difference was not a new name or a completely new design. It was the removal of assumptions that realistic trials should have challenged before the war. The weapon finally fulfilled its promise. It did so only after enemy ships had completed voyages they should never have survived. The image of a perfect torpedo hit seems simple. A submarine calculates the target S-course. The crew sets depth, speed, and gyro angle. Compressed air launches the weapon. Its engine drives it through dark water. The wake reaches the enemy hull. Impact should settle every remaining question. For the Mark 14, impact sometimes began the mystery. The weapon had already survived launch and followed the correct bearing. Its depth might finally be accurate. Its magnetic feature might already be disabled. The target might be broad, stationary, and only a short distance away. Still, one small assembly could prevent the warhead from functioning. That contradiction made the contact defect especially revealing. The closer an impact approached the ideal perpendicular angle, the greater the deceleration became, the greater the deceleration. The more likely the mechanism was to distort and bind. The shot that looked best through the periscope could create the worst conditions inside the exploder. No specification table would make that weakness obvious. It emerged only when the weapon met a real hull at operational speed. The same principle applied to the earlier defects. A depth setting was not the weapon's actual depth. A successful exercise run was not a successful combat detonation. A sophisticated magnetic concept was not dependable merely because its physics were plausible. Each assumption required proof from the complete system. The crews supplied that proof at enormous risk. They carried defective weapons through mined approaches and defended sea lanes. They closed targets protected by aircraft and escorts. They remained submerged while depth charges shook machinery and lighting. Then they returned with reports that often challenged official confidence. Those reports were not always precise. They could not be. Combat is a poor laboratory. But repeated uncertainty is itself important evidence when the pattern remains consistent. Lockwood's tests succeeded because they turned uncertain observations into visible mechanisms. A torn net showed where the torpedo truly traveled. Enemy messages showed where explosions occurred relative to their targets. A disabled tanker allowed repeated impacts under nearly identical conditions. A steel plate reproduced the force that trapped the firing assembly. The solutions became clear once the questions became measurable. Correct the depth control. Abandon the unreliable magnetic function. Lighten the contact firing pin. None of those steps required a more dramatic warhead. None required greater range or speed. They required the weapon to perform its basic sequence consistently. The Mark 14's story also warns against judging military equipment through isolated specifications. On paper, the torpedo combined speed, range, guidance, and an advanced influence exploder. Those qualities suggested superiority. In combat, reliability multiplied every other quality. When reliability approached zero, theoretical performance mattered little. A slower or less sophisticated weapon that detonated could be more useful. Once reliability improved, the Mark 14's existing strengths became valuable. The same torpedo that embarrassed American submariners became a major instrument against Japanese shipping. Its reputation changed because its behavior changed. That distinction matters. Later success did not prove the early criticism wrong. Early failure did not mean every part of the design was worthless. The evidence supports both conclusions. The weapon possessed strong underlying capabilities. It entered war without adequate full system validation. Its defects were then recognized too slowly. The final cost cannot be expressed through one precise number. It includes wasted torpedoes and surviving ships. It includes patrols shortened after ammunition was exhausted. It includes commanders judged through results their weapons could not reliably deliver. It includes fuel and cargo that continued toward Japanese bases. It also includes the risks accepted during repeat attacks that should never have been necessary. Tonan Maru Number 3 became the clearest symbol because the variables nearly disappeared. The tanker had stopped. Tinosa had closed the range. The crew checked its solution. Wake after wake ended against steel. 11 warheads remained silent. The tanker survived. The final torpedo returned with the submarine. That preserved weapon carried more persuasive evidence than another optimistic test report. It represented the moment when a combat failure could finally be brought home, examined, and reproduced. The Mark 14 was repaired because submariners refused to treat repeated failure as coincidence. They challenged a trusted system with observed results. Engineers then translated those results into mechanical corrections. By early 1944, the weapon was finally serving the crews who had depended upon it since Pearl Harbor. The perfect hit could now do what everyone had assumed it always would. It exploded.